In this course, I will introduce you a linear algebra course that is not a standard course of algebra, but a singular one that contains some topics that you will probably have not heard about before and that you will have difficulties to find elsewhere. More, you will be surprised by its power and the beauty of the results. I will give some details next, and if you think that it is worth the trip, come with me to discover how linear algebra can help us to deal with and solve beautiful and practical problems. You are invited. In a standard course of algebra, we studied linear combination of vectors, that is, linear spaces. We also study other things like matrices, determinants, intersection of subspaces, etc., and also system of linear equations. In this course, we study non-negative and convex linear combinations, that is, cons and polytopes, and system of linear inequalities. I think that it is difficult to find how to solve system of linear inequalities, so I invite you to see how to do it. In the course, we start by describing polytopes and cons, and apart from the definition, from the theoretical definitions, we try to give some pictures for you to have an intuitive idea of what cons and polytopes are. I think it is very important for the student to have a graphical model for these structures, because it facilitates the understanding of the theory. The concept of dual or polar cone of a given cone is very important. First, we need to know that given a cone, we can find what is called the dual cone. We will define that, and this will be the main element in the course, because we are going to give an algorithm that, given a cone, will give us the dual cone. And based on this algorithm, we are going to solve all the problems that we will state. So we have the Gallman algorithm, and then we can study if a vector belongs to a cone. It is not an easy problem because we have inequalities. We can solve system of linear inequalities. We can obtain the dual cone. We can solve subsystems of a given linear system of inequalities. We can reduce a cone to its standard or minimal form, or a polytope to its standard minimal form, etc. One important thing is the following. Linear spaces are cones, but not every cone is a linear space. So the first interesting thing is that any linear space is a cone. You know that a vector in a linear space can be written as linear combinations of the basic vectors. But if a linear space is a cone, it can be written as non-negative linear combinations of vectors. Of course, immediately you can think the following. If I have a basis for the linear space, I can duplicate the vectors, and I take the basic vectors but change sign, and then I can use non-negative coefficients to write any vector in the linear subspace. Because when it is positive, I use the basic, and when it is negative, I use the other vectors with sign change. However, there is an interesting question. Can all the vectors of a linear space be generated with less than twice the basic vectors? Fortunately, the answer to this question is positive and very surprising. It's surprising because this can be done with only one more vector. If the linear subspace has dimension n, with n plus 1 vectors, we can write any vector using only non-negative coefficients. And I am going to tell you this new vector, how is this new vector to be added to the basis. this vector, that there are several possibilities, infinitely many solutions for that vector, but I am going to give you one. If you add all the basic vectors and change sign, that is, you generate the b, which is minus the sum of all basic vectors, this is the new vector that you need to add in order to allow you writing any vector in the subspace with non-negative coefficient. I think this is a very interesting and surprising result. In the course, we are going to define the dual cone of a cone. What happens if the cone is a linear subspace? In that particular case, what happens is that the dual cone is the orthogonal subspace. So, the dual cone of a linear subspace is its orthogonal subspace. This means that the dual cone is a generalization of the orthogonal subspace, which is interesting. Another interesting result that you will see in the course is that any cone can be written as a linear subspace plus an acute cone. An acute cone is a particular case of cone in which generators, when change sign, do not belong to the cone. If you take a generator of a cone and that generator change sign belongs to the cone, then the cone is not acute, otherwise it is. Okay, then any cone can be written as the sum of a linear subspace plus an acute cone. And the linear subspace can be given with a basis. It's better to give a basis because it is the least number of vectors that can be given to define the subspace. And the acute cone can be given by the edges. That is the minimal representation that you can give of a cone. The important thing of the algorithm that you will learn in the course is that it always gives you the dual cone in the standard form. The linear subspace is given as a basic with the basis, and the acute cone is given by the edges. Okay, and how to obtain the intersection of two cones? The problem of intersection of two cones leads you to solving system of inequalities, which is a complicated one. However, we can do one thing. We can write the intersection of two cones as usual. Let me explain you that what A pi means. A is a matrix which has some columns, and the pi is a letter, a Greek letter, that refers to non-negative linear combinations. A sub p means the cone generated by the columns of A. That means pi 1 the first column plus pi 2 second column plus pi n the nth column. So A pi intersection d pi is the intersection of the cones A and D generated by these matrices, by the column vectors of these matrices. I can write this intersection as the polar of the polar or dual of the dual, because the dual of the dual or the polar of the polar of a given cone is the initial cone. It's similar to the case of the orthogonal of the orthogonal that gives you the initial subspace. So I can write this intersection in that way, but that permits us solving the problem, because this tells us how to obtain the intersection. Because what you need to do is first to obtain A pi, its polar. You obtain the polar of the cone A pi, and then you obtain the polar of A pi in D pi. That means that you use the algorithm twice. The first time to obtain the polar of A pi, and the second to obtain the polar of that subspace in D pi. And how to do this? Instead of starting with the identity matrix in the algorithm, you start with the generators of D pi, the cone generators or the acute cone generators. So, interesting thing is that if you use a new classes that are the duality or polarity classes, you can see the intersection in this new form. Let me now explain you how to solve a linear system of inequalities when this is a homogeneous system. That is, when all the independent terms are zeros. The idea is to write that system, which is the traditional way of writing the system, in a different way, in such a way that we can see polarity or duality in some way. The idea is to see that the first equation is the dot product of the vector a11 equal to a1n times the vector of unknowns x1, x2, xn, and that less or equal 0. Then we have the dot product. But now it is not equal to 0, it is less or equal 0. And the definition of dual con is precisely this. This means that x1, x2, xn is the dual con of the con generated by the row coefficients of the system. So the interesting thing is that this new way of seeing the system of inequalities tells us that the solution of that system is a con, which is very important. The solution of any linear system of inequalities is a con. And second, it tells us that is the dual con of the con generated by the row vectors or coefficients of this system. And that is a very important thing. It is interesting to see that when we try to solve one linear system of inequalities, we use the algorithm, we pivot several times, and we get a final matrix. And in that final matrix you contain enough information not for solving any possible subset of this one, but some subsets in some order. You can solve the first inequality, the first and the second, the first, the second, and the third, and all the equations, but not any combination. But you can solve many of them, because the last matrix has information to see how the dual cons are. In those examples, in the right column, you have some matrix with the row subindex, that means linear combination of those columns. And you have also another matrices with the pi subscript, that means that this is a con generated by those columns. So you have the linear space part of the solution and the con part of the solution. What happens if we have a linear system of inequalities? Then not all the coefficients are 0, and then you create a new unknown, xn plus 1. You multiply the right-hand side terms by xn plus 1. You move them to the left-hand side, as indicated, and then you get a homogeneous system of inequalities. But in order that system to coincide with the one below, you need to add that xn plus 1 should be 1. So this tells you that what you need to do to solve the system is, first, you need to solve the homogeneous system, and then taking only the solutions that satisfy the last equation, which is xn plus 1 equal to 1. And similarly, when you solve a system, you can solve different subsystems, but always in order. In the case of compatibility of these systems, we are going to study a particular case. We have equalities, instead of inequalities, but all the unknowns should be non-negative. Although this appears to be a very particular case, we can demonstrate, and we will do it in the course, that any system can be transformed in this form. And then we write the system of equations in the other form. The system above is exactly the same as below, but the system below tells you that the column vector b1, b2, bm is a linear combination of the column vectors obtained from the linear system of equations, of inequations, in this case equations. And then, because the x are all non-negative, that means that these equations means that the column vector belongs to the con generated by this cone, to the cone, not to the linear subspace, to the cone, because the coefficients are not negative. So this is the way of solving these systems and to analyze the compatibility. In this table, which is very interesting, you have the general structures that you obtain when you use system of equalities, homogeneous or complete, and system of inequalities, homogeneous and complete. You can see that with equalities, you obtain linear spaces and affine spaces. And when you have inequalities, you get cones for the homogeneous case, and you get, in general, polyhedron. I define a polyhedron here as the sum of a linear space plus a cone plus a polytope. It is very interesting to discover that any linear system of inequalities is equivalent to a polyhedron. That can be, you can get particular cases in which you don't have linear space, or you don't have cone, or you don't have polytope, but the general form has the three components. It is also very interesting to obtain the faces or the facets of any dimension of a polytope of a cone. The algorithm, in addition to giving the dual cone of a given cone, gives you all the facets of any dimension. In reality, you have at the end of the algorithm the facets of dimension n minus 1. By intersection of that, you can obtain the facets of any dimension. This is very interesting and will be described in the course. And finally, I want to end with an example, a very interesting example of a water supply problem that I have used many years to explain to students. Consider a water supply problem. You have two deposits, and then you need to distribute this water at different points, and you use some pipes. And the problem is, first, what are the equations? What are the unknowns? The students have difficulty when you have a real problem to reproduce the problem mathematically, and sometimes they don't know what equations to use, what unknowns to use, so that it is interesting to see that in this case, the unknowns are the water circulating in each of the pipes. Because we have 15 pipes, we have 15 unknowns. X1 is 2 up to x15. And what about the equations? The equations are establishing a balance of flow and correspond one equation to each node. Because we have 12 nodes, we have 12 equations. And the equation says that the water entering the node should be equal to the water exiting the node. And that's all. So we have a system of 12 equations with 15 unknowns. This can be written in matrix form or can be written anyway. But the important thing is that because it is a complete linear system of equalities, we know that the solution is an affine space that has one particular solution plus a linear space. So the only thing I need to do is to obtain a particular solution, to determine the dimension of the linear subspace, and then to obtain a basis. In this case, I have demonstrated a theorem that says that the dimension of the linear subspace is equal to the number of holes in the water supply network. In this case, we have a network that has only 4 holes. So 4 is the dimension of the linear subspace, and then I need to define a basis that is 4 vectors. And the interesting thing is that I can identify immediately the basis, or the basic vectors, which are associated to the different holes. I can consider the first hole. I can consider that there is no flow in the rest, there is no flow entering or exiting the network, but it's only circulating in that hole. And then I write this vector, which I assume that the circulating flow is unit, and depending on the directions of the flows and the rotation, this can be +1 or -1, and then the remaining unknowns should be 0. So the first column can be easily obtained, and the same with other holes. Finally, I have to obtain a particular solution. This particular solution can be any one. You can choose any. There are infinitely many, and you can choose any one. So the idea is, if you need an amount of water at a node, you say, okay, I take this from this deposit, and I take it by this way. You take this way, and you put the corresponding unknowns, the value that correspond to the water you want to get from that node, and the rest zeros. Then you do one by one all the nodes where you want to get the node, and you add up all the results, and you will get that particular solution. So my students are asked to design a different water supply network. Every student has to take a different one. They will have different holes, and they will have different dimensions. They will have different basic vectors, and they will be able to calculate it, and they will calculate also the particular solution. So without using the algorithm, only with mathematical knowledge and engineering knowledge, they are able to write all the equations, and look what a beautiful result. These are all possible ways of taking the water from the deposits to the consumption nodes. There are no more ways, all are there. You can choose any value for row 1, row 2, row 3, and row 1, and row 4, and you have all. You can see all the solutions, which I think it is very nice. However, you discover that because you have linear spaces, the rows are real numbers, but they are not bounded. So you can get solutions in which you have pipes that should carry flows very, very large, which has no sense. So the problem is that we have a mathematical problem that do not correspond to the real case, and we need to limit the capacities of the pipes. Then we need to add that any pipe xi, the amount of water circulating in that pipe, should be less than the corresponding capacity ci. And if the water is circulated in the contrary direction, should be larger than minus ci. So I need to add to the previous equations these inequalities, and then what I get is not a system of equations, but a system of inequalities. Okay, I end this with this example, and you have seen that this is not a standard course because it includes new elements such as cone and polytopes, and especially a system of linear inequalities together with the obtention of facets of cones and polytopes. You already know about an algorithm that permits solving very important problems of linear algebra in a simple way. You also know that the knowledge of the set of all feasible solutions and the corresponding structure permits obtaining immediately all optimal solution of linear programming problems. If you think that this material could be relevant to your work, and you want to incorporate the knowledge of cones and polytopes to your way of facing problems, you are invited to learn, enjoy, and discover a new world following this free course.